right, so let's take a look at section 11.6. Okay, so 11.6, as I said, is on counting the number of ways we can do something. Sometimes when you count them, order matters. Sometimes it doesn't. Right, yeah, so this part, if anyone's heard, we do have discrete mathematics here. It's usually for juniors. And if you take that class, part of what you study is on combinatorics, okay, or counting. Okay, all of our answers today are going to be integers because we're counting the number of ways you can do something. So you're not going to get decimals. Okay, you couldn't get like 3.5 ways of doing something. Okay, and if you can count how many ways something can happen, then you can start to get into probability. Okay, we're not going to get into probability, but if I know there's 10 ways something can happen that are favorable to me, that I would want, and there's a total of 1,000 ways it could happen, then I have a 10 out of 1,000 chance of what I want happening. And if I divide them, I could get the percent, okay, and figure out what are my chances. Right, so one thing that's kind of neat to do, I don't think we're going to have time, but if you have like a scratch ticket and they say the odds of winning, we can actually figure out, is that correct, what they said, and it should be. We could say, all right, there's this many ways we could get numbers on a scratch ticket. There's this many ways we could win, and then we could figure out our odds of winning. All right, let's look at this example. Okay, I want to know how many different ways can I arrange the letters A, B, C, D to form 3-letter codes. So in other words, you can pick any 3 letters you want at a time to make a password. The approach to this kind of problem would be to do it systematically. Okay, this is small enough that we can actually list all the possibilities. So you'd want to start by just taking 3 letters and list every possibility with those 3. Okay, so what would be 3 letters to start with? Yeah? Yeah, let's take all the ways we can arrange ABC, including ABC. You want to just try to do this in an organized way. Don't just start guessing, otherwise you'll forget what you might have done and not done. So the next thing I would do is keep the A first, but just switch the C and the B. Those are all the possibilities you can have with A first, using these 3 letters. How about putting B first? What are the 2 possibilities I could have if I put B first? Yep.
B, A, C,
Yeah. And how about if I put C first? Mike?
C,
Yep. And it turns out, for any 3 letters you pick, there's 6 ways to arrange them. All right, so if you pick ABC, there's 6 ways. If you were to pick ABD, there's 6 ways. So what I'll do across the top is I'll just write down 1 of each combination. We don't have to go through all 6. So we could pick the A, the B, and the D. There'd be 6 ways. What are 3 other letters I could pick? Pick the A, the B, and the C, the A, the B, and the D.
A, C, D.
All right, we could pick the A, the C, and the D. Yep, I don't think we had that one. And there should be 1 more.
B, D, and C.
Let's see, B, we have B, D, and A. Yep, I don't think we have B, D, and C. All right, so there's going to be 6 ways, or a total of 24 different ways to pick. You got 4 letters, pick 3 at a time to make a password. Okay, and if you wanted to go through and list them all, just try to do it systematically. The next one I would do here would be like ADB. Okay, and start with B and use the other 2 letters, A and D, D and A. And then start with the last letter we haven't started with, D. And then pick the other 2 letters, AB, BA. And you could go through and do all of them. You get 24 different permutations. Okay, that's what that's called. Any questions on that? sometimes when we list out possibilities, listing is good. Sometimes a diagram, like a tree, is also good. Okay, this is sometimes called like a decision tree. Each time you make a decision, you kind of branch off in that direction. And then if you have more decisions, you branch off of that. So let's look at this one. So an animal is going to perform 2 tasks. Okay, for each task they perform, they can get one of 3 rewards. So I want to know how many different sequences of rewards could the animal get? How many different ways? How many? Count them up. And now they've said something kind of important at the bottom. Each reward can only be given 1 time. Okay, so once you pick that reward, if they get that reward for doing the first task, they cannot get that reward again for the second task. That reward is gone now. All right, so let's start with task 1. So the animal performs the task. How many different rewards could the animal get at this point? After they perform the first task?
3.
3. Let's call the rewards A, B, and C. Maybe they get reward A, reward B, or reward C. Now, at this point, they're going to perform task 2. Whichever reward they got, they're going to perform the second task now. If the animal got reward A, what are the 2 choices left for rewards? Yeah?
B and Z.
Yep, they either get B or they get C. Okay, how about in that part of the tree? Either they're going to get reward A or reward C. And how about the last part? A or B. Yep. So how many different paths are there to follow? 6. Okay, there's 6 paths here. So the question was, how many sequences of rewards are available? 6. Now, if the rewards could repeat, then that would be different. After the animal got reward A, then they could get reward A, B, or C again. And after they got reward B, they could get A, B, or C again. So in that case, you could have up to 9. Okay, any questions on that? So you see these kinds of trees, there's a lot of different uses. Sometimes, like if you're troubleshooting a problem on a machine, they may have a chart like this in a book. Is the machine plugged in? Yes or no? If no, plug it in. If yes, okay, continue to the next step. Is the screen on? If yes, do this. If no, try this. So you can kind of troubleshoot different problems by looking at a diagram like that. Okay, but what's the problem with this approach? Either a tree diagram or making a list. Either one of those approaches. Yeah?
Human error. You could forget some.
Okay, you could forget some. Definitely that's possible. What else?
Very time consuming.
It's very time consuming. Okay, imagine, you could have a tree with millions of branches. Imagine I gave you a problem about license plates. And I said, I want you to pick, there's four spaces on the license plate, and they're all letters, and the letters could repeat. So now you have 26 choices for the first letter, and then no matter which letter you pick off of that, you have 26 more choices, so the tree is going to get huge. So it's not always practical. All right, so this principle is going to help us to figure out some types of problems where you have to count the number of ways something can happen. Right, so this is called the fundamental counting principle. And basically it says that if you have A ways of making your first choice, okay, you have B ways of making your second choice, and C ways of making your third choice, then total number of possibilities is A times B times C. And it assumes that A, B, and C, oh, I'm sorry, the choices are independent. So let's say you're getting lunch. And A represents the drink you choose. Maybe you have 4 choices for a drink. B represents the meal you can pick, and maybe you have 6 choices for the meal. And C represents dessert, and there's 3 desserts to pick from. All those choices are independent of each other. If you pick a soda for your drink, that doesn't mean you can't pick ice cream for dessert. They're all separate choices. In the dog problem with the rewards, those choices were connected. If you pick choice A for the first reward, you can't pick a certain choice for the next rewards. Okay, so that problem was a little different. All right, so if this was the case, 4 drink options, 6 meal options, 3 dessert, you just multiply all this together, 4 times 6 times 3, and that's how many different meal combinations you could make. Drink, meal, dessert. And you can extend this to as many choices as you have, okay, as long as all the choices are independent of each other. Meaning, picking one doesn't limit your options for the later choices. Okay, any question on that idea? It's called the fundamental counting principle. All right, so let's look at a license plate one. Okay, so we're going to make up some license plates that have 2 letters followed by 3 digits. Now you cannot have any repeating letters or numbers. So we have to take that into account when we make our choices. How many license plates can be made? Okay, let's start with the letters. Okay, if you pick a letter for the first spot, how many choices do you have? It's the very first thing you're going to pick. First letter.
27.
How many?
27.
27? Does everyone agree with? How'd you get 27? I'm just trying to think if you're thinking of something that I'm maybe not thinking of.
How many letters there are?
Yeah, how many letters there are? 26, right? My English isn't that good, so I'm going to trust you guys. Is it 26? I might have said 27 too. I'm a math guy, not English. So we got 26. Now, be careful what it says right here. No repeating letters or numbers. Okay, so the next letter, we can still use this principle. Okay, but we just have to make sure that we take into account can't repeat. So no matter which letter you choose, how many choices do you have left for the next letter? Nick? 25. And we've taken into account if you choose C, well, you can't choose C next. Okay, so you only have 25 left to pick from. Doesn't matter which letter you pick. You have 25 choices left. Okay, and now the next 3 are going to be digits. How many choices do we have for digits? For the first digit. I'm a math guy. I know this one. Yeah. 10. Okay, 10 digits, 0 through. It's assuming you can use zeros. Maybe on a license plate they might not use 0. I don't know. It might look like an O. So if there's other restrictions like that, we're not going to worry about that. So we got 1 digit. How many choices for the next digit? Yep.
9.
And the 3rd digit? 8. So basically, if you multiply all that together, that's how many different options there are. Okay, so you can make 468,000 license plates. Yeah, I mean, it's quite a few. But I mean, even if you think of like New York City, they couldn't use this system. It's not enough. You know, they need a version of license plates where you can go at least in the millions. So, same with phone numbers. Phone numbers, you could figure out in theory how many possible phone numbers are there in the U.S. system. European numbers are different, but in the U.S. system, you've got the area code that's 3, then the local code that's 3, and then 4. So you got 3, 3, 4. But some of those might be reserved. Okay, you probably can't have a phone number that's like 000000000. That's probably one that they don't use. Probably, can anybody think of a prefix that you couldn't have for a phone number? It'd be very bad if you had this prefix. Well, that might be bad luck, but this one is actually 911. So you couldn't have an area code that was 911, because the second you dialed that, you wouldn't be able to dial anything else. It would go right to 911. So then you'd have to think out, yeah, you gotta, so if you counted up every possibility, then you'd have to eliminate every possibility that begins with 911, count all those out, and there might be other special things you gotta cut out too, like all zeros, all ones, all twos, things like that. Okay, so it gets a little more complicated with real life restrictions, but you don't have to worry about that for us. Okay, we have 8 runners in a race. Okay, I want to know how many ways the runners could finish. Does the fundamental counting principle apply here? Yeah. As long as we take into account once one runner finishes, the number of choices we have after that. Okay. Every problem I usually do like this, I usually just put blanks to represent either the positions on a license plate or the position of the runners. It just helps me to visualize it. How many choices do you have for the first runner? You have 8 different people that could come in first. Okay. Now, after that runner finishes, how many choices do you have left for the second place? 7. Okay. And all the way down. And what are we going to do with all these numbers? Multiply them. What is that really? We've talked about this before. This is 8 factorial.
8.
Yeah, exactly. All right, so if we plug in 8, do I have factorial?
Yeah, it's next to it.
Next to 7, there we go. So there's 40,320 ways it could be finished. So now you could figure out the probability if somebody said, if you predict the exact order that these 8 runners finish in, maybe you win a prize. Well, you have a 1 out of basically 40,000 chance of predicting it perfect. Now, if somebody just said, predict the top 3, you got a better chance of doing that. Okay, to predict the top 3 runners, you have a 1 out of 333, if I type that right. That's a lot better odds to predict the first 3. Okay, and based on the chance or the probability of getting it right, that might control the odds. Okay, so like on different kinds of races, they have odds, and it can get complex, but for now, we're just going to count 40,320 different ways.
So if you're like betting on horse races, you have no chance of winning. You're just throwing money away.
Well, the chances of you winning, it's all based on probability and statistics, like casinos. Mathematically, you can look at any game, you can figure out that what the odds are of winning. And the odds are always in favor of the casino, which basically means long term, if people keep playing, the casino is guaranteed mathematically to make money. Now, every now and then, somebody wins, and that's kind of what hooks you, right? You get that chance, and then you win. But I guarantee if you played on average, for 50 years, mathematically you're going to lose money. The odds are in favor of the casino. So if you win, sometimes people stop because they win, they say, you know what, I'm all set. And you can also use a lot of calculus to analyze probability. It gets a little more complicated than what we're doing. Okay, so in the last 2 examples, we used the fundamental counting principle, either to find out how to arrange letters and numbers in a license plate, or names of finishers in a race. Okay, these are all called permutations. Okay, so the important part is the sentence right here. It says a permutation of n elements is a specific ordering of those elements. Okay, has to be in a specific order. Okay, if Mary, Sue, and Joe finish a race in that order, that's different than Joe, Sue, and Mary. Okay, different order, that's different positions in a race. So the order makes a difference. License plate, if you have a license plate 223, that's different than 322. same numbers, but it's a different order. Okay, phone numbers, passwords, all that kind of stuff. Order is important. Okay, so any question on what a permutation is? It's a specific ordering. And we saw this one in the example of the runners. If you have basically n elements, and you want to know how many ways can you arrange them, it's n factorial. We didn't see that on the license plate because we had 26 letters, but we didn't have 26 spots for letters. If you did, then it would be 26 factorial, assuming letters are not repeating. Right, so if I had 3 markers and I want to know how many different orders can I put black, green, and blue, you can just think of it as a letter problem. Well, black and blue, they have the same letters, so that'd be confusing. But ABC, how many different ways can you arrange ABC? It's the same idea. It would be 6 ways. Right. Now, sometimes we only want to order a subset of those elements, meaning, I've got 5 things, and I only want to know if I pick 3 of them. Okay, it's kind of like the first problem. How many ways can I put them in order? I think we did 4 letters and picked 3. Okay, that's a subset. You're only allowed to pick 3 out of the 4, any 3 you want, and put them in order. Okay, so the next one says you have a group of 15 people. Out of this group, you're going to pick a president, vice president, and secretary. So basically, you're picking 3 out of 15. How many different ways can you do this? Right, so you've got 3 spots available. How many choices do you have for president?
15.
You have 15 different choices. Now, once you pick the president, how many choices would be left for vice president? 14. Because you can't have the same person be president and vice president. If you ever had a question on a test about can I allow the same person to do 2 things, just ask me. But generally, when you have a group like this, the president, the vice president, and secretary are all distinct, usually. And now how about the secretary? 13. Okay, this is kind of like picking the top 3 finishers in a race. It's the same idea. So if you had 15 people, how many different ways could you pick president, vice president, and secretary? 2,730. Now, this is an example of a permutation because the order is important, but you're only using a subset of R elements in the permutation. Okay, so this is called an R permutation. So basically what we just did, R was 3. 3 out of 15. And we can use this symbol, NPR. Okay, so that symbol is basically a short way of writing down, I want you to do a permutation. You have 15 things to pick from. You're allowed 3 at a time to pick. And it turns out you can just use this formula. Let's do example 5 again using the formula. So the notation would be, we have 15 objects to pick from. And we're going to do a permutation, picking 3 objects at a time. So it says you can do 15 factorial over n minus r factorial. 15 minus 3 is 12 factorial. Now, you wouldn't want to type this in because a lot's going to cancel out. When I write out 15 factorial, everything from what down cancels out. Right, because this is 15 times 14 times 13 times 12 all the way down to 1. And this is 12 times 11 times 10 all the way down to 1. So all you're left with is 15, 14 times 13. which is exactly what we just did. So, any questions on that? And next part, we're going to look at how many 5-letter codes can we make using the entire alphabet. Okay, so this is a permutation, because if you're making passwords or codes, the order matters. So we're using the entire alphabet. How many total choices do we have to pick from? Sam?
26.
26. And out of the 26 letters, Lasan, how many at a time are we picking? 5. Okay, so basically that's n factorial over n minus r factorial. When you do out the numerator, everything from 21 down is going to cancel. So you're left with 26 times 25 times 24 times 23 times 22. So this is pretty big. If you have 26, so this is just a password that's 5 letters long. Now, we also assumed here, what kind of letters are we using? Think about passwords.
Either all capitals or all lowercase.
Right, we're doing either all capital or all lowercase. So if you did a combination of capital and lowercase, you can double 26 to 52, because capital is different than lowercase. And then if you decided to throw digits in there, you get 10 more choices, so then you have 62 choices. And then if you throw in special symbols like question marks, you got even more. So there's literally, infinite number of passwords, depending on how long you want it to be. There's trillions and trillions of combinations. So that's how many you have just picking 5 letters out of 26. So about 7.8 million. Extremely easy for a computer to figure that out, though. 5-letter password, a computer could figure out in seconds, just by trying each one fast enough. It's not until this number starts to get into like quintillions and really, really big that it starts to take a long time. That's why they say don't pick passwords sometimes shorter than like 7 letters. A lot of like bank websites, they won't let you pick something that's 4 or 5 letters long. You got to pick something a little longer. Okay, and last thing we're going to look at is a combination. Okay, so this is a counting problem that looks at the number of subsets that can be formed from a given set of elements. In a set, we don't care about the order. If you have a set of markers, red, green, blue, yellow, I don't care what order they're in inside the box. If you give me the box, I have the whole set. It doesn't matter what order they're in. Okay, so order doesn't matter. As I said earlier, poker hand. Order that you get your cards in, somebody's just going to give you 5 cards and they get 5 cards. It doesn't matter the order you get them in. If you're forming a committee, okay, that's a key word. If you see committee, usually a committee is just a group of people. Nobody has a specific position, or like a board of directors. Everyone usually has the same position. Just a group. So this one says, how many committees of 3 people, or how many committees, if you have 4 people to pick from, pick 3 at a time, how many committees can be formed? Easy way to do this is let the people be letters, A, B, C, D. Now we did this same problem before as a permutation. You had 4 letters, pick 3 at a time. Okay, who can give me one committee that could be formed from the people A, B, C, D? Yep. You could pick A, B, C. Now, there's nothing else you can do with A, B, C. If you pick C, B, A, those are the same 3 people. The order you pick them in doesn't matter. So there's one. What's another committee you could form besides A, B, C? What's that? You could pick A, B, D. Okay, a couple more.
BCD?
You could pick B, C, D. And there should be one more. Raina? A, C, D. Looks good. So if you have 4 people to pick from and you want to make a committee, there's four different ways you could do it. Okay, so in that example, we chose 3 people out of 4 to make a committee. And we use a similar notation to permutations, but we use a capital C instead of a capital P. Or we can write it like this. Where have we seen this before? Yeah?
Pascal's triangle.
Right. Okay, we did this notation earlier. It says n factorial over n minus r factorial. This is a binomial coefficient. So all of Pascal's triangle is numbers that are useful in combinations. So I guarantee you, if you go in Pascal's triangle, look at the 4th row, 3rd column, you'll find the number that we just did in the last problem. Just remember, if you're going to use the triangle, you always start with row 0, column 0. So if you had 12 things and you wanted to pick 5 at a time, look at the triangle, go to row 12, go to column 5. That's how many ways there are to do it. This formula is much more practical, though, because as you get really big, you don't want to have to list your triangle out all the way to infinity. Okay, so there's the formula we've had before. If you have n objects, you want to pick r at a time for a combination. It's n factorial over n minus r factorial, r factorial. This will be our last one. Okay, so we have a basketball team of 12 players. How many different starting 5 players could you have? And where the order of the starting players doesn't matter. That's the starting 5. Right? Since order doesn't matter, it's a combination. It's a combination of 12. Choose 5. Both of these notations are fine to use. Neither one of them, though, does the calculation, which now we have to do. So it's n factorial over n minus r factorial. So 12 minus 5 is 7. Times r factorial. Okay, when I write out the factorial in the numerator, everything from what number down is going to cancel? Sam? 7. 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2 cancels with 7 factorial. Denominator, 5, 4, 3, 2. Everything in the top should cancel with everything in the bottom. So we got, make that a 1, make that a 2. Make that a 1 and a 2. We could do, let's see, make 3 a 1. Make 12 a 4. And cancel the 2 with the 2. So you're left with 4 times 11 times 2 times 9. Okay, so if you had 15 people and you wanted to pick the starting 5 players, there's 792 ways to do it. Any question on the difference between permutation and combination? All right, so the homework, it's on 631. Okay, 1 to 5, 7 to 12, 14 to 19, 21 and 23. So as I said, test tomorrow. On the test, there'll be 1 inductive proof, and then the rest of the test will be on combinatorics.